All right, good morning, folks. I appreciate you tuning in and watching this lecture remotely today. I need to travel to Minnesota this weekend to partake and be a speaker at the American Physical Society's annual conference. So, we're going to have to discuss a few important things so that I can get through all the material in this course, and I really appreciate you guys watching this remotely today. To that end, part of your assignment for this week, or I guess the entirety of your video assignment, is going to be responding to some points in this lecture, but I want to open that up more to these bigger questions that we've been talking about lately: black holes, space time, some of these concepts that are really tricky to wrestle with and are extremely interesting, but seem to be lacking and full of mystery. And so, if you want to address any of those topics, I'm going to put a final pin in our story of galaxies today with some of the least understood phenomena, which gets us back into black holes. But we're going to be talking about active galactic nuclei today, which are a special case of galaxies that seem to have something really, really energetic happening at their center. And the reason that we wrapped last time with the Hubble expansion and that we're not continuing with that immediately is because the story of active galactic nuclei and the interpretation of where they're located and what they are is largely dependent on interpreting the redshift of these constellations of bodies or whatever the heck is going on, right? The redshift of these galaxies associated with these active galactic nuclei. So we need to take a break and talk about these very strange anomalous redshifted objects, which we call quasars. Now, quasars, turns out, are going to be a central part of our discussion today. So let me just real quick review what we'll talk about. We'll talk about quasars, which are a special case of active galactic nuclei. Let's just call them AGNs. It's a real mouthful calling them by their full name. And I want to talk about some potential hypothetical mechanisms that could underpin them. Now, of course, the possibility remains at the end of the day that the reason that we see these very strange and extraordinarily energetic and bright phenomena at the center of these galaxies is because, well, physics breaks down and reality stops making sense. There's this rip in space-time and we have a supermassive black hole. But there might be some other possibilities, some of them more mundane, some of them perhaps even more tantalizing. We're going to talk about it's hard to talk. We're going to talk about galactic magnetic fields at the end, which is something I've been studying a lot lately and talking to some astronomers down at Stanford that are working on this, and it's a brand new science, which is really interesting. So what I'd like you to do in your response is consider some of these alternative processes. As we're reformatting this course for next year, a big portion of the program is going to be about considering alternative hypotheses to what is the standard narrative in the textbook, because this is like the really creative element that seems to be sort of bleeding out of science right now. And I want to find a way to get you guys, when you're young and just starting off on your careers, maybe a few of you will become scientists, but I want you to start exercising that muscle in your brain that allows you to think of creative solutions to problems, even if you're wrong. So the idea is to think about all of the possibilities that could explain these phenomena. Maybe some of them are good, maybe some of them are bad, but we need to generate some ideas. Otherwise, we have to accept that physics just stops working at some point. And, make up your own mind about that, but it's a little untenable for me. So let's look at this special case. I'm going to try to keep this as brief as I possibly can in order to get us caught up so that we can continue next Thursday. But it all comes down to the fact that there's something really strange happening at the center of certain galaxies. So what's going on? Now, the discovery initially came with these phenomena, which they dubbed quasi-stellar radio sources. This is where you get the contraction quasar from. It basically just means something sort of like stars, but not quite like stars. Now, this happened right after World War II because, of course, all these radio technologies were coming online, mainly to fight the war, but the astronomers started using them as well. And they noticed that some of the radio sources were in the same location as these really faint blue stars. And no kind of star that anyone knew about in our galaxy would emit such powerful radio frequencies. So they obtained the spectra from these faint blue stars, which had, somewhat common emission spectra, namely the Balmer series that we talked about at the beginning of the lecture series. But there was something strange about the spacing of the Balmer series. It seemed like all of the lines were shifted really far to the red. Now, if you just attributed that to a recession velocity, right, that this galaxy or whatever it was, or this quasi-stellar object was moving away from us really fast, it boggled the mind how that could be possible, because it was moving at some very significant fraction of the speed of light. And that's problematic because accelerating material that fast is almost energetically unimaginable, especially to the people first studying these. So these objects that appeared star-like but had this really strong radio emission was then joined with another set of objects that also had this really star-like appearance, these high redshifts, but also no radio emissions. So they kind of grouped these all together, and they started examining them in other bands, infrared, X-ray, and called them, as a class, these quasi-stellar objects, so quasars, QSOs. If we take a look at some of these things, we see that, well, they look a lot like stars at first glance. You can see on the screen we've got a picture from the Hubble Space Telescope. And it's thought that one of these two bright quasi-stars in the middle is actually in our galaxy, but the other two are 9 billion light years away. And we'll talk about how they come up with these distances in a little bit, because that's actually really critical to this discussion. Now, all the spectra in these quasi-stellar objects show redshifts, and none of them ever show blue shifts, which is really interesting. Because what it turns out is that the quasars are associated with some sort of emission from the center of these really active galactic nuclei, right? The center of galaxies. But quasars turned out to be the particular name that we gave to the ones that were pointed right at us, so we could get a nice view of them. Which is strange because, we're going to start looking at the fact that these active galactic nuclei emit these really powerful jets of radiation. And these jets, though they're pointed directly at us, still appear to be redshifted, which is really strange, because if they're emitting a lot of particles and subatomic materials and whatever directly at us, well, we would think that it's coming towards us, it would be blue shifted, but that's not the case. And so this starts to cloud the discussion of where these things are, where they're located, right? Because if you think back to our last lecture, we were considering the distance ladder, and we said that if you want to find the distance to something relatively nearby, you can use a pretty standard parallax method, right? You can use these binary systems to set up some sort of triangulation and get a pretty good estimate of the distance to that binary system. And that's really as far as it goes with direct observations. Beyond that, you start having to use these things called standard candles, right? You need to start making assumptions about what kind of object you're looking at. Is it a giant mag light, or is it just a birthday candle? And if you know which it is, and you know how bright it is, then you can estimate exactly how far away it is. Now, this gets compounded even further, because at some point, we're not able to see these nice supernovae, we're not able to see these nice Cepheid variables that can give us this hopefully reliable standard candle to get that distance estimate. We're actually looking at the Hubble relationship, that is, that things that are far away have high redshift, and we're converting that into distance. So you see a high redshift, you think that's far away. And these are some of the brightest objects. These quasars are some of the brightest phenomena in the sky, right? But they're also really high redshifted. So we think this is an interesting contradiction of terms. Normally when we see something bright, we think it's close by. But then we have this Hubble relationship where things that are far away must be redshifted. So we have bright things that are highly redshifted. And it creates a real conundrum, because you're talking about an energetic process that is far beyond the scope of anything that we see happening in our local part of the universe here in our galaxy. It's just an unimaginable feat for something to be so bright and so far away. And the hinge of that comes down to the question of how far away are these things really? Because, of course, some components of the redshift may very well be attributed to their distance in this whole Hubble landscape, the Hubble redshift landscape. But there seems to be some component of intrinsic redshift which clouds the discussion a little bit, and we'll see more and more of that as we go forward. So some of these redshifts, by the way, if you just attributed them to recession velocity, so how far it's moving away, we're talking about velocities somewhere in the neighborhood of 96% the speed of light. And that's just almost unimaginable. Remember that if you accelerate something, you need an energy that's proportional to that. And as you approach the speed of light, you need an unending amount of energy, essentially, to move something past the speed of light. It seems to be the limit by which those materials can actually be dislocated from whatever gravitational web they're locked into. I think that a reasonable analogy is thinking about it as the actual deformation of that medium that they're all embedded in, right? So if you want to use space-time, that's fine, but you're talking about it has a stiffness to it, right? Whatever is holding atoms to one another, and whether it's just structures from the atom themselves, it doesn't matter. There's some deformability of that, which is limited. You know, if I slam my hand down on the table right now, there's a wave of deformation that's going to travel through the table to the other end of the table. It has a speed limit to it, right? The atoms in the table can only deform and get out of their lattice position so fast, right? The same is true with the air. When I'm making sound, it's hitting the microphone right now. The air can only relocate itself and host those waves in a particular fashion which is commensurate with material properties of the air molecules themselves. So something is causing us in the universe to experience this absolute limit by which something can move. And what's really crazy is that these redshifts, if they are just Doppler recession velocities, are something approaching the speed of light. So that seems untenable. There must be something else going on. And I'm sorry if this is somewhat confusing, because we really want to be able to say something certain, right? We'd really love to say that every time you see a redshift, it's a recession velocity, or every time you see a redshift, it's an expansion coefficient, right? For the actual distance between objects in mass for the universe getting bigger, right? This is the idea from Lemaitre and the Big Bang, that everything's just kind of moving away from it, from some central point. But neither one of these seem to account for it perfectly. So even if you go with some combination of the two for this redshift, you have a lot of freedom in which one you have to accept, because you need to see that there's some limit as to how fast these actual bodies can move, that these particles, these really high energy nuclei that are being ejected from the center of these galaxies, how fast can they really move? So something else is going on, and we're going to try to get to the bottom of that. I hope that we can get closer to an answer for it, but I'm afraid there's no simple solution that has been proposed yet, other than, of course, supermassive black holes, which essentially amounts to physics stops working at some point at the center of the galaxies. So, you know, people first started looking at these and asked questions about whether quasars obeyed Hubble's law, and that those really large distances were actually implied by the redshifts. And we see some examples here. So top left shows a quasar that's at the heart of a spiral galaxy that's about 1.4 billion light years from Earth. Bottom left shows another one that's in an elliptical galaxy, some 1.5 billion light years from us. In the middle shows some remote pairs of interacting galaxies. One of them harbors a quasar. And, you know, people started studying these, and one of the first people to really point out that there might be some problems with this Hubble estimation of the distance of these quasars was this guy who was actually one of Hubble's students, a very precocious young student, very, very smart and very much a go-getter. And he ended up kind of making himself a bit of a persona non grata in the institutions he was working at, because he started cataloging these quasars. And he created what he called an Atlas of Peculiar Galaxies in 1966. And what he found initially was that a lot of these things we were calling quasars seemed to be linked by trails of dust and so forth to nearby galaxies close to us. So I guess it's worth mentioning at this point that most of the quasars that we're talking about are really far away. And this brings up the question, why don't we see any nearby us? And are the quasars actually close to the galaxies that we associate them with? And HARP seemed to think that there was reason to believe that they weren't necessarily spatially locked to the galaxies that we had been deeming them associated with. In other words, the quasars might appear at some distance, right? If there's a jet at the center of the galaxy, that the quasars could be mistaken for being at the galaxy if they overlaid it in some way, right? So if the jet was interacting and there was some energetic process happening in front of the galaxy, that you would mistake it for being part of the galaxy that was behind it. Now, he kept looking at these, and he found that there was often very high redshift quasar activity that was very different redshift than the galaxy that we were associating it with. So this contributed to his suspicion that this redshift wasn't actually something that we could truly associate with the Hubble relationship or with velocities per se. There was something else going on that was causing the spectra of these atoms, right, that we're looking at, the vibrations, the light spectra, to be shifted red that had maybe nothing to do with this beautiful distance relationship or this beautiful Doppler effect. Something else could be going on. Now, today, and of course chemists know that chemistry often does alter the line spectra in very interesting ways, right? So when you actually recombine atoms or you rip them apart, you can actually get a modification of that atom such that its spectral frequency does shift in interesting and predictable ways. But this is, of course, work that's going on outside of astrophysics as far as I can tell. So now, if we do accept that the reason that these high redshifts are there with these quasars is because they're really far away, then there must be a truly impressive amount of energy that's going on at the center of these galaxies. If they're actually at the center of the galaxies and they're really, really bright, they're outshining the whole galaxy, they're making these galaxies look like they're right next door, but they're really, really far away according to the redshifts, then we have to consider that something really crazy and super energetic must be going on. Now, if that isn't the case, and these are actually much closer, or the quasars are in some sense the really bright quasi-stellar business that we're seeing is ejected from these galaxies, but actually quite close by to us, then we have a totally different program to be looking at. Now, there's been a number of papers published over the years that are in some sense picking holes in the standard model of quasars, which I want to be absolutely clear of, is that these galaxies themselves host the quasars, right? The quasars are at the center of the galaxies. But there's some problems with that. There seems to be some overdensity of redshifted quasars in the field around our nearby galaxies, right? So, in other words, these high redshift quasars seem to be aligned with one particular axis of the redshifted active galaxies. And there seems to be bridges of gas between the galaxies and the redshift galaxies. This is kind of similar to what Harp was arguing, that they're associated with galaxies that don't have the same redshift as them, right? That are perhaps more nearby. And this is problematic for lots of reasons because they're supposed to be of the same objects. This is one paper which I recommend you might check this out. It's called On Quasar Host Galaxies at Tests of Non-Cosmological Redshifts. Now, one possibility with that is that the host galaxies are actually in a transition, right? So we talked last time about how most standard cosmology imagines that the galaxies all formed at the same time and that they are not really we're not going to really see new galaxies forming at any moment. But one possibility that's creeping into the mind of people is that the quasars are actually some moment in the evolution of galaxies. Now, of course, because of this redshift relationship, the thought is that, well, all these quasars are far away, therefore they're in the distant past. Therefore, yeah, quasars could be an important moment in the evolution of galaxies, but it's something that happened in the distant past only, right? So it reinforces the idea that there's a linear timeline to the universe, that it had a start, that it's progressing, and it eventually will end in some sort of cold death of everything. We're all going to be swallowed by black holes and so forth. But again, how reliable is that distance narrative, right? Another paper I wanted you guys to check out, if any of you are interested in following up on this. It's called Anomalies in the Counts of Low Redshift Quasars. This one points out an interesting point. There are some galaxies that actually appear to have some inherent blue shift alongside their redshift. So some of the different atoms, right? Some of the different spectral lines, those particular frequencies, are actually shifted towards the blue, which is really strange. And the thought is that this could, in some sense, be confusing the distance ladder as well. Now, most of the quasars with inherent redshift, right? So ones that can't be ascribed to distance per se. So there are some quasars that are pretty close to us, and those have redshifts as well, but we can't possibly say that they are due to Hubble relationship or anything like that. So the authors of this paper are really putting out a call for people to study these quasars that are in this redshift range, right? This somewhat low redshift range, but still anomalous with respect to their distance. So people will use other methods with these nearby galaxies, some of the other more proximal sources on the distance ladder, to gauge where these things are, and they see these intrinsic components. So the idea is we need to reach out into our imaginations and really pick at what could be the sources of intrinsic redshift. And I would suggest to you that chemistry may play an important role in that. There's also the discussion of galactic magnetic fields, which we'll get to at the end of this, and I'll hopefully have time to follow up more with that when we do our review at the beginning of class next Thursday. So the textbook goes through next how we can gauge the size of these objects. So this is actually quite interesting as well, because when we're talking about how energetic something is, in some sense we're talking about the density, right? So how much luminosity is happening in a certain region. And the way that they do this is they look at the difference in how long that light takes to travel from one side of this quasar to the other. And what they find, is that they're really small. So, I think that the distance estimates that they come up with these, let me see if I have this written down here. The idea is that the quasars actually, the difference in the light traveling from the far side to the near side is something like a few light months, right? So not huge distances, right? Now, of course, we measure the size of the center of a galaxy on the order of light years, right? So how far is a light month? Well, Pluto takes something like 5.5 hour light. The light from Pluto takes something like 5.5 hours to reach us. And the nearest star is something like 4 light years away. So really, really small. So closer to on the order of within our solar system boundaries. I think that's a reasonable way of thinking about it. If you think about the edge of our solar system, like the Oort cloud, as being maybe a light year or two away, then we're talking about something really, really small. So a couple of light months for all of this brightness to be contained within this distance is extremely, extremely small and dense. All of this activity is happening in a very small place, according to this differential light path travel model. So really, really energetic. And of course, what's interesting is you also see these jets associated with it, right? You find these nuclei and these gases are moving actually within some percentage, some small, maybe 2% of the speed of light. So there's actually stuff being kicked out of the center of these galaxies emanating from these quasars. In at least some of the cases where this is not always seen. And of course, there's contradictions to this as well, right? Where you see that actually the jets and the redshift associated with where the jets are pointed at these galaxies is very different than the quasars themselves. Now, in order to find a common model for what's causing these quasars, we should probably review the characteristics of these things that we've been talking about so far. So they're really powerful. They emit more power and radiated light than all the stars in a galaxy combined, which is just completely bizarre. And of course, it's within a narrow distance window, right? Really, really small, something on the order of a solar system. Now, another thing to consider is that quasars are often observed to be shooting out these pairs of straight jets at close, at these almost light speeds in a tight beam to distances that are far beyond the galaxies in which they originate. And these jets themselves are a really strong source of radio and gamma radiation. And because the quasars put up so much power in such a small region, they just really can't be conceived of as being powered by anything like stars, like nuclear fusion or fission or any of these processes that we've examined so far. There's nothing we can think of that would be that powerful in such a small unit of distance, right? Now, it's interesting. So at this point, the textbook makes this claim. It was only evidence of the existence of black holes that accumulated that it became clear that only supermassive black holes could account for the observed properties of quasars and AGNs. So this is interesting because we know that the biggest elliptical and spiral galaxies all have these nuclear bulges. There's a lot of stuff going on at the center. And when your textbook says that evidence of the existence of black holes accumulated, what they mean is that they can't think of a mechanism gravitationally by which all of that material would be swirling around the center at such incredibly high speeds. Remember, in our solar system, something like Mercury is going really, really fast compared to, well, something like Pluto, right? This is the traditional gravitational worldview for how things orbit. The problem is we know that galaxies don't obey this nice gravitational path. We know there must be something else going on, right? This is how we get into things like dark matter, right? It seems like there's something else happening. Now, it could be that there is really an exotic form of material that we can't detect. This could be represented by dark matter. It could be a really cold, mundane kind of material, like a bunch of dead stars or a bunch of really cold old moons and planets. I mean, have to be an extraordinary amount of them, right? Very cold, almost boggles the mind, given the 14 billion year given the 14 billion year birthday that we've set on our universe, how you could cool that much stuff off so quickly. Or it could be that there's something else besides gravity playing into the cohesion and rotational dynamics of galaxies. And I think that's a really intriguing possibility as well. But if we assume that gravity is the only player here, then we are essentially left with some anomalous structure at the center of the galaxies. And that's essentially how we get to this idea that we must have an extraordinary amount of stuff crammed into an impossibly small space, right? And that's what we're looking at with the standard model for these quasars and active galactic nuclei. We're looking at an extraordinary gravitational source at the center, which is giving off which is causing some sort of super energetic reactions to glow. Now, this is interesting, though, because the black holes themselves, right, by definition, light can't escape from these things, right? So it can't be the black hole itself, even if we admit that these black holes, these rips in our understanding of physics, are an actual thing. It's like we know that by definition that light can't escape from. So the only possibility is that the stuff outside of this anomaly, outside the actual limit of the black hole, is causing all of these collisions of material and this swirling and ripping apart of stars and just crazy chaos to ensue. And that acceleration of all that material is actually what's glowing and leading to something that we see in the quasar. And I think this is actually quite compelling, that there is stuff moving really, really fast. We can actually tell that from radial velocity measurements. And it does appear to be super ionized. One way to counteract all of this would be to think of it as a superstar almost. And what you're seeing is the corona of that superstar. Now, the superstar is not and what I mean by superstar is really just a bunch of stars that are all just squished together. Now, if we treat stars like they're balls of gas, then of course, if you have that much gas in one place, it's going to collapse because ideal gases can collapse indefinitely, and you're going to get this physical anomaly called the black hole. But if stars actually do have a lattice structure, which kind of seems like they do from the continuous spectrum, right? They have that nice black body spectrum. If stars do have some sort of lattice, if they have a material basis that's not gaseous, something more liquid-like, at least at the photosphere, then you find yourself in a very different position where you can actually join a lot of these little droplets together, and you might be able to get something at the center of galaxies that is very much like a superstar. So, you know, again, the only reason we don't think that there's superstars at the center of galaxies is because all of these collisions would lead to mergers, and the mergers would lead to too much gas in one place, which would collapse. If the stars aren't made out of gas, then the most likely solution is that these active galactic nuclei are something like superstars. If you go back to our discussion of the formation of stars, you'll notice that when these stars are being formed, they also have these enormous jets. These protostars also have enormous jets that look very much similar to the jets coming out of these active galactic nuclei. So there might be something to that. Now, the jets themselves aren't black body radiation. So we're actually talking about something analogous to the corona, right? The atmosphere of the sun, which is full of all this ionized material. The body of the sun itself does have this thermal heat spectrum, but that's not what we're talking about with these jets, right? So it's really an intriguing possibility that what we're seeing here, and here's a good picture of it, is that you have actual something that's very much approximating a star formation process that's happening right there at the center, which is leading to, as this swirl happens and as this dust and debris forms the arms of the galaxy, that it shields the emissions from that enormously reactive spinning soup. And the energy is only preferentially emitted along the axes of the disk because, well, that's the only place it can flow in and out of. Now, oftentimes it's preferentially, I mentioned this earlier, it's often preferentially emitted from one pole versus the other. And I think we have to really start considering the presence of magnetic fields in order to explain that. So, I guess it's worth mentioning too at this point that we don't see anything like this from our own galaxy. And the question, that opens a whole new can of worms. This is actually a model of our own galaxy here where we don't have an active galactic nucleus in our own galaxy. And we'll talk about the models for why that is next week when we start to examine cosmology. But if we want to think about why there might be a preferential direction for the emission of these jets, I think that magnetic fields are probably going to teach us a lot. Now, magnetic fields are really, really poorly understood. This is actually a completely brand new science, and there's been a couple of really exciting papers about this lately. You know, the idea previously has been something like, well, the magnetic fields in the galaxy are pretty weak on balance, right? You know, they can hardly achieve even the magnetic field strength cohesively of our own Earth, right? So how in the world could they be important in anything? And what it comes down to is that they're more closely viewed as a layered structure, something like an onion. So this is another paper I think you guys should check out. If you look at the actual arms, so this is a top-down view here in the upper left of a potential model for the magnetic organization of a galaxy, what you see is different streams of conductive material that are going almost opposite one another, and there's different layers. So what you have is that the galactic magnetic field, in some sense, going back to this sort of simplified picture on the previous slide, you have some rings which are rotating in one direction, the magnetic field, the magnetic effect is going in one way. You can think of these as sort of toroids or donuts. And then in other elements of the galaxy, and say in other rings, they're going the other way. And the effect is that the magnetic field on balance seems to cancel out, which makes them very, very difficult to see when you're looking at something far away because all of those individual fields sort of blur out into one giant sort of weak magnetic field. But the possibility remains that actually the individual components of that could be quite strong. And what this might have the effect of doing is, in some sense, focusing all of that energy, all of the emissions from the center of these galaxies into these cones, right? These beams of charged particles that that led to the discovery of these quasars in the first place. And I think a good way to think about that hypothesis is something like cathode ray TVs, right? And you guys are probably way too young to remember this, but when I was a kid, all the TVs were these huge, heavy objects, right? And the way that they would work is you would actually generate some current flowing in this really rarefied, they call them vacuum tubes, but they actually have some atoms inside of them, right? And these ionized atoms, in some sense, are conductive, and you can control the column of ionized atoms with this magnetic system. And so what you do is you can draw these little pixelated structures across the back of the screen. Now, something very similar might be happening with these jets, as far as I can tell. But this is such brand new science that I don't think anybody has the answers to that. If you want to follow up a bit more on these topics, there's a really good textbook here that I've been referencing lately. It's called Cosmic Magnetic Fields by Roni Keppens, Oliver Porth, and Hans Goldbled. Now, this is a very, very, very new field of research, and I don't know how it's actually going to rewrite how we understand these things. But it's certainly worth following up on. Now, beginning of class next time, we can talk a bit more about how these magnetic fields work. I want to maybe take a moment to refresh how magnets in general work, because that's a really poorly understood thing. But what I'm trying to build towards here, and what we're going to work towards next week, is this idea that galaxies might metamorphosize over time. That just like the life and death of stars, we might have a life and death of galaxies. Now, if the Big Bang hypothesis holds to be true, then we should be seeing only a unidirectional version of that metamorphosis. Galaxies were all formed at some distant point, and they evolve, and they sort of die and peter out. But if we have a really long time for the universe, maybe if we have no time limit for the universe, if it's always been here, then we should be expecting to see moments in the evolution of individual galaxies. Much like with stars, we can see, main sequence stars moving off the main sequence, something approximating the death of stars, right? And these nova and so forth, or white dwarfs. So we're going to start turning these concepts towards a story for galaxies themselves. Now, of course, this is the absolute utter reaches of our knowledge about the universe, and it's going to wrap towards this cosmology that we've built over the last 50, 60, 100 years that tells a story of the universe. And all these little pieces are slotting into it, and I hope that you're getting some sense for the uncertainty at each step along the way. And you can see how it's very easy sometimes for science to have these complete revolutions where we revisit something that's fitting into our model, and we say, wait a second, if these quasars are actually a counterexample to the Hubble relationship, and they're much closer than we thought, and they have high redshifts, then what does this redshift business mean all of a sudden? Maybe we have to consider a very different model for the evolution of the universe. So I'm going to stop there for today. I appreciate you guys tuning in to this kind of awkward and bizarre remote lecture, but it's the best I could do. I really needed to go and give this talk this weekend. So please respond on Flipgrid, give me some thoughts. Tell me what appeals most to your sensibilities and to your imagination. And maybe, dig in, do a little bit of research and see what other alternative explanations you can come up with for quasars. I would really appreciate hearing about that. And otherwise, have a great weekend. Have a great week, I guess. And I will see you guys on Thursday.